Hello and welcome to S6. This is my 6th sequential circuit video. And in this one, we're going to be talking about asynchronous 3-bit counters, or just, I guess you could say asynchronous counters in general. And that's what's in front of you, is this asynchronous 3-bit counter. And so for designing this counter, and I can actually just kind of show it working real quick. It counts from 0 to 7 on this negative edge triggered design. That's really just what it does. So the way that I designed this was that I was actually referencing a 4-bit asynchronous binary counter that we got for this assignment, and then you just make the 3-bit counter basically out of that. And the only difference in between these two really is so this is all my bits from least to most significant. And if we want a 3-bit counter instead of a 4-bit counter, well, instead of having another T flip-flop and then all this cascading stuff going on, you can just connect it to ground. Because, well, a 3-bit number is just a 4-bit number with a 0 in the 4th bit. And the reason that I have to include that 4th bit is because a lot of these adapter things, like this BC to 7 segment little device, it'll only take 4 bits as an input. And so it's not like I can just have 3 bits and it'll just be able to accept it. It has to be 4 bits. So you just connect it to ground, and then everything after that is effectively the same. So I showed how this circuit works. This is the unstrobed circuit, and I'll define that later. But notice in this one, it's just like straight. It's a straight counter. It just works perfectly fine. However, typically with counters, you'll encounter something called a glitch. And basically, what a glitch is that when switching in between different numbers, there will be moments, very small moments in time, where the wrong output will show. So, for example, if you're switching from, say, 1 to 2, it would go 0, 1, 7, 5, 2. So that it'll like flash like 2 or 3 random numbers before going to 2. And that's because all of the signals are still propagating through the device. And so there will be moments in time where, again, it'll be incorrect. And that's because, that's because of the propagation. There's propagation delay. Say hypothetically that each of these gates has a 50 nanosecond propagation delay. Well, that means that, this one goes, it takes 50 nanoseconds to process, and then it goes through. This is another 50 nanoseconds, and then another 50 nanoseconds, and then we get our output. So there are moments in time where, say, this toggles and it flips to a different value, and these two are still the same because the inputs for these devices depend on the output of these devices, of the devices higher up in the cascade. And so in that way, glitches can occur. And most typically they occur from going from an odd number to an even number, because when you go from an odd number to an even number, all of the the bits closest to the most significant bit need to change. So when you switch from an odd number to an even number, say this bit down here might have to change. This would represent the 3rd bit, so that would be like 4. Say that we're going from 5 to 6. Well, 5 is just oh, that's not like the best example. Let's going from 3 to 4, and then we'll say going from 3 to 5, or from 4 to 5 rather. So from 3 to 4, well, 3 is just going to be this 1, 1, 0, and 4 is going to be 0, 0, 1. So in that case, every single bit changes, and so in that way, there's going to be more propagation delay because everything needs to change. But it's not even necessarily that everything needs to change, it's that the most significant bit needs to change. And when the most significant bit needs to change, that will lead to the greatest amount of delay. However, the number of glitches will be dependent upon the number of bits that need to change. Yeah. And then, let's see. Oh, and then from 4 to 5, well, it's 0, 0, 1 for, looking from top to bottom here. It's actually 1, 0, 0 for 4. But if we wanted 5, it would be 1, 1, 0. Or 1, 0, 1, sorry. So if it's just 1, 0, 1, the only bit that needs to change is this one. So there's almost no delay. It's 50 nanoseconds. Whereas this one is 4 times the amount of delay, or 3 times the amount of delay. So when you switch from an odd number to an even number, there are generally more glitches in delay in the correct output than switching from an even number to an odd number. See, this question is, if you use 5 flip-flops instead of 3, how high could you count? Well, you could count to however far you can count with 5 bits in binary. So with 4 bits, you can count to 15, 2 to the 4th, and then with, I guess 2 to the 4th minus 1. It's 16 values. It just goes up to 15 because we include 0. So with 5 bits, it would be 2 to the 5th minus 1. So we'd be able to count to 31. Alright, so now we can look at our strobed circuit. This is the same thing, except it's attached to a controlled buffer. And what that does is that on every half clock pulse, it will output like a null value. So we can actually just look at it. So notice how in this one, every time we go down, it turns off. Then we go back up, the count is incremented. And that's because of this controlled buffer here. And what that controlled buffer does is it says, okay, well, when this input value is low, it outputs a null value. It's like it's not 1 or 0, it's just X. It's just it's not high or low. But then when this is on, well, this increments and this is able to see a value. And in that way, it's supposed to reduce the number of glitches that happen. So yeah, that's what strobing does. Let's see. Oh, they're called high impedance states. There we go. And this control buffer is also known as a tri-state buffer, so that's important to know. But yeah, basically, this whole process is called strobing, and this buffer here is what allows you to actually do that strobing. So yeah, I believe that's all. Let's see here. All right, that's all. Thank you for watching, and I'll see you in the next one. Bye-bye.